So today we will be discussing the paper Intriguing Properties of Neural Networks. James would be presenting for and I would be presenting against. So this is the presentation overview. We'll look at some paper information, the summary, which includes the terminology used by the paper, and the two intriguing properties. One is which the adversarial attacks, and the other one is the semantic information in units. And then we'll look at the strengths of the paper, weaknesses, and maybe some discussion. So the paper goes like this. It was submitted in 2013. It was revised again in 2014. It's 10 pages long. It's cited over 6,000 times. Although it looks intimidating, it's not really that difficult. So these are the authors. These are fairly well-known researchers doing active research. And if you could see the citations, it's 100K, 200K. So the terminology in the paper is slightly confusing. They refer to unit, which is actually a neuron. It's a standard term in literature. And the other one is the distortion. In regards with the adversarial perturbation, distortion is measured by the standard deviation of the pixels, which is the clean image minus the adversarial image squared, summed over, and then take an average. And this is the standard deviation.
So you are lowering down your sound.
Yeah, I'll try to keep it up. Yeah, so the first intriguing property is regarding the adversarial attacks. Until this point, the assumption was that the classifiers are fairly generalizable and then they are fairly robust. But the finding from this paper is that adversarial examples do exist. Adding carefully curated noise to the original images would actually alter the classification output of these neural networks. And then the second finding was that the semantic information in the units are neurons. So the assumption was that the neurons in the neural networks try to separate features, try to learn independently different features. But the finding from the paper is that this is not maybe true. We'll look at each of these things carefully. So for the adversarial attack, they come up with this attack algorithm called LFBFGS. So if you try to recall, Dr. Shah has already touched upon this in the second lecture. So it's a white box attack. It's slow and it's a targeted attack. So it goes on like this. So there's a perturbation R. We try to minimize the perturbation R such that when this R is added to a clean image X, and then sent to the model F, the output needs to be L. L is the class, which is not the original label. So we're trying to alter the label such that the perturbation is minimized. Also, we need to make sure that the original image plus the perturbation lies in the range of the image, which is bounds of the image, which is 0 to 1. So this minimizer R might not be unique because we could have multiple such perturbations. And then this makes the problem really hard. To simplify this, the authors have come up with an approximation of this original problem by combining these two constraints, where they try to minimize the C times R and the loss of the function with the adversarial input and the label L, such that the distorted image still lies in the range of 0 to 1. And this is optimized using the line search algorithm. So this is the proposed adversarial attack algorithm. And then this algorithm is used on various models and shown that adversarial examples do exist. So for that, they show this table. If you could see the first column, they consider 6 networks here. The first 3 networks are FC10, and the value you see in the bracket is the lambda, which is the weight decay parameter, one of the hyperparameters for the model. So they consider 3 different hyperparameters for FC10, and then the fairly complex model, 2 complex models, and then the autoencoder model. So they consider 6 different models and try to attack these models with the proposed attack algorithm on the MNIST dataset. So what they found out is that these adversarial examples do exist, and they were able to achieve a 100% fooling rate on the MNIST images. So the final column shows here the minimum distortion for each network required to completely fool the network. So other takeaway here is that the larger the lambda, the larger the perturbations. So the authors here were trying to change the hyperparameter lambda to sort of include regularization in the network and to see if they could still get the adversarial examples. But increasing the lambda here, as you see from 10 power minus 4 to 10 power minus 2 to 1, has definitely increased the average minimum distortion. That is making the attack more difficult. But on the other hand, larger the lambda also means the accuracy is less on clean images. So if we try to increase the lambda, the test error keeps increasing. So the training error and the test error here are on the clean images. So at this point, we are convinced that classifiers are not robust. We have succeeded in generating these adversarial examples. So the next question here that arises is, can we transfer these adversarial examples to a different model? Say we have generated adversarial examples on one particular model and then try to send these adversarial examples to a different model. Do they transfer well? This was the question. And then to support this, they've given this nice table. They've again considered the 6 models, which we see on the first column. And then each other column is for the same 6 models to see how this cross model generalization of these adversarial samples work out. So adversarial images on the same model turns out to be 100%, which we have already seen. So we have FC10, we have generated adversarial samples. So it has a 100% fool rate on the same model. So this is consistent across all models. So if you try to attack one model and send the same images again to the same model, we get a 100% fool rate. So now we try to see how these adversarial samples try to behave when sent to a different models. So consider the third model, which is FC10. We know that FC10 gives a 100% fool rate when sent to the same model. But what if we send to FC10 10 power minus 4, the first model? So it gives out a fool rate of 71.9. This means 71.9% of the time, these adversarial samples were still valid, which is quite interesting. Um, so is this consistent across all the models? Maybe only sometimes. Let's see one more example. The first model, which is FC10 10 power minus 4, when adversarial samples was generated on this particular model, and then sent to the fourth model, which is FC 100 110, only 2% of the time it was able to transfer well. All the other 98% of the time, the model was able to predict correctly. So at this point, we can say that attacks transfer to different models, but it's not always the case. It's just sometimes. And then if we see that these 3 models here are fairly complex, and then when we try to transfer these models, the accuracy is low. I mean, the fool rate is low. So for fairly complex models, the fool rate tends to be low. And then just for the comparison, they've given 2 rows in the end, which is just random Gaussian noise added to the images. It's around 5 to 10%, which we can say that it's still much less than these values, which are obtained by our optimization algorithm.
So Rahul, one point here is that these models, all these models were trained on the same data set, right?
Yes,
The same data.
yes.
So
On
that's
the same data
important
set.
distinction. I
Yes.
see. Okay, good.
Yes, all these are trained on MNIST. So at this point, we can answer this question that sometimes these adversarial samples do transfer to different model. But the question here is, all these are trained on same MNIST. So obviously the patterns and the learning thing would be the same for everything. So what if we try to split the data set? What if we train the models on different subsets of the data set? That was the second question. So if we could transfer to different model, and what if there's no training overlap? What if these models are trained differently on different subsets of MNIST? So this was the second question they tried to address. So for that, they've come up with this experiment. They come up with three different models here, and these three different models are trained on different data sets. The first model is trained on P1. P1 and P2 are two different subsets of MNIST, each having 30,000 images. So the first data set here was trained on P1. The first model was trained on P1. The second model was trained also on P1, while the third model was trained on P2. So here we could observe that, when trained on P1, the error was 0%. So it was learning fairly well on the P1 clean image dataset. And then P2, when tested on P2, it's giving 0% accuracy. So it's learning really good. But when it's tested on the test set, which is also a clean image dataset, it's coming out to be 2%, which is fairly a good network generalization, we can say. The first model is trained on P1, but when tested on the test set, it gives a 2% error, which means it's fairly generalizable. And then the last column here is is the minimum average distortion. So the minimum average distortion required to completely fool these networks. So these are also similar. So we can say that all these networks are consistent with these numbers. So the next experiment here is that we're trying to generate adversarial samples on one network and then try to test it on a different network. So what we see here is, first, these two models are trained on P1, as we have already seen. And the third model is trained on P2. And similarly, the columns, these two columns are regarding the models trained on P1. The third column is the model trained on P2. So what we see here is, how well do these adversarial samples transfer. So for for the first model, it's 100% when tested on the same model. But when tried to transfer it from the first model to the third model, it was just 5.9%. Again, the first model was trained on P1. The third model was trained on P2. We see a transferability of 5.9%. And similarly, for the third model, when tested on P1 and the first and second models, it's 8.2%. So at this point, we can say that attacks do transfer to different models when there is no training overlap. But it's not maybe always the case. Let's see the second part of the table. So the obtained adversarial samples are amplified to see how well do they perform. So when they're amplified to standard deviation of 0.1 and then sent to the third model, we see an increase in the fooling rate. It's 43 and 22. And similarly, for the third model, it's 27 and 50. So what we can say here is, so when the adversarial samples are tried to, when they're amplified, we see a higher fool ratio. And then when they are sent in as in, we see a slightly lesser ratio, like 5 to 8%.
So Rahul, I have one question.
Yeah.
So in the top one where you have cursor now,
Yeah.
So when I look at the first row, you say 100%.
Yeah.
So that is 100% is what? Is it a fooling rate, or what is 100%?
It's the fool rate or the test error. So the error is 100% or the fool rate is 100%.
Full rate is 100%.
Yes.
So you generate these adversarial example for this first row, and then then you taste it that it's successful. And now when you do for the second column in the first row, so it is much lower, 26%, but still it works. But
Yes.
when you go to third one, which is a different partition, right?
Yes.
So then it's not that successful.
Yeah, it's not that successful.
So from here, so can you repeat what's the conclusion from that first block of these three rows? That it transferred.
Yeah, the conclusion here is the adversarial samples do transfer to different models when there is no training overlap, but to but not to that great extent. It's just 5 to 8%. So it's so there's
Which
still
means they are not effective, that much effective,
not that
right?
effective. Yes,
Yeah. Okay.
not that
So
effective.
that's the main point. So I mean, reasonable thing will be to look at the second column. So they do 26%, and which is okay, but just 5%, which is pretty bad. Okay, good. Yeah, continue.
Yeah, for the second question, we can say sometimes it does, sometimes it doesn't. So it's fairly not that effective. So the next question here is why? How can these attacks exist? Why do these attacks even exist? Can we try to explain them using some mathematical formula? So for that, the authors give this really nice section 4.3, which is titled Spectral Analysis of Unstability. So let's say we have an input X and then the weight matrix W1, and then let phi denote the output of some layer. Let phi1 denote the output of the first layer. So when we try to send in the input image X with some parameters W1, the output would be phi1 of X. Then this output is sent to the second layer, which is the phi2 of X, and then so on. So if the network has k layers, so the output of the neural network phi of X would be this particular thing. So we try to explain the instability of this neural network, the output of this neural network using the Lipschitz constant. So it goes on like this. For some particular input image X, and then for some particular perturbation, we try to calculate the difference of the output at some particular layer K in the neural network. So we see that the difference in the output when given a clean image and then the perturbed image is always bounded by L times R. L is the Lipschitz constant, R is the perturbation here. And then when we try to generalize it for all the K layers here, we get this really nice expression. The output of the neural network when sent into clean image, which is phi of X, minus the output of the neural network when sent perturbed image, which is phi of X plus R, is always bounded by L times the perturbation R. Here the Lipschitz constant L is the product of all the Lipschitz constants for each neural network layer. And then to better understand the Lipschitz constant, it is just the largest slope. If you try to see this picture here taken from Wikipedia, this purple line denotes the function f, and then we have x and the y axis. So the Lipschitz continuity, so if some function is, if it's Lipschitz continuous, we try to say that there's always a function, there's always a constant L, um, which is, which is, which we can say that the slope of this function f is always bounded by this Lipschitz constant L. So if you try to move this R to this left-hand side, we get this difference in the response of the function divided by the difference in the input response, which is basically the slope at point X and point X plus R, which is always bounded by this constant L. So we get this really nice cone sort of thing.
So talk about the positive, negative before you go there.
Yeah,
Why
yeah.
there are two lines here?
Yeah, so the upper bound here is the positive L, and then the lower bound would be the negative L. And if we try to plot these two, we get these two lines. One is the positive L and the negative L. And then when we try to run this over the function f, we always see this, see that this function always lies in this pink region. It never goes into this cone. So the L actually shows the slope of this cone. So one is the positive L, one is the negative L.
Because we are taking the absolute value of
Yeah,
that
we are taking the
on the
absolute.
left side. Okay, good.
Yeah, so after discussing this, they come up with this table. So they try to develop a neural network. They try to test it on MNIST. And then they try to calculate this Lipschitz constant at each layer. So they see that for the first layer, it's 2.75. For the second layer, it's 10. Third layer, 7, so on. So if you're trying to calculate the Lipschitz constant for the complete network, it would be the product of all these numbers. So the takeaway here is that we see this instabilities very early in this network. So the first layer itself, we see an upper bound of 2.75. Um, the second takeaway is that this upper bound doesn't really prove the existence of adversarial examples. It just proves that there are instabilities in this network, and then but it doesn't really prove the existence of adversarial examples. But what we can do here is we can try to reduce the upper bound. We can try to reduce this upper bound, which in turn reduces the instabilities in the network, and then we can try to limit these attacks on the network. Yeah, so for this question, how can these attacks exist? The authors try to explain it by giving this explanation by trying to formalize the network instabilities. And then James would take over to discuss the other intriguing property.
Yeah, so we've covered the adversarial attack portion of the paper. So the second portion of the paper discusses semantic information in the units. The assumption was that units are separate features, and the finding for this section of the paper was that maybe this isn't the case. So this actually goes back to a couple papers published before this, where the authors had analyzed individual units by finding the images in the data sets which maximizes that particular unit. So they were analyzing a hidden unit by collecting the images the unit likes. More formally, it's denoted here, where X is the input image, EI is the natural basis, phi is the layer activations for some arbitrary labor, and then you take the dot product of that, and then the images which maximize this are the images that the unit likes. And in those papers that were published previously, it appears to work quite well. So here are a grouping of images, and they all seem to have some similarities. So in this case, they all are similar in that they all have lower round strokes. So those papers would describe that this unit is sensitive to those lower round strokes. And likewise for ImageNet, these images all share the property of being similar to white flowers. So describe that this unit is sensitive to white flowers. However, this paper challenges that by replacing the natural basis with a random vector. So the only change is the vector that's getting multiplied. So instead of only using one unit, now you have a random combination of units. And this also appears to work well. So here is a grouping from the MNIST dataset where all these images appear to have upper straight strokes or lower round strokes. So it'd be described that this direction instead of a unit, so this direction is sensitive to those things. And likewise for the ImageNet, this direction appears to be sensitive to white and spread flowers. To go over this in a more mathematical sense, here we have two graphs, and it's showing that the individual units aren't complete. So they aren't, on their own, they aren't telling the whole story. So red, we have unit 1, and green, we have unit 2. Now, looking only at one of those units, we would get a local maxima. So we get images that would be around this local maxima, and same with the green unit. However, the more useful local maxima is the local maxima of the network, which is a combination of those two units. So the real feature would be following the black arrow. And although it's possible to have this local maxima, or the network local maxima align with the axis, it's not likely because these spaces are really large. So in conclusion for this section, they got the same results for maximizing single units versus multiple units. And this suggests that the semantic information is spread among those units. So it's not specific to a particular unit. And they conclude that this method that other papers had used, it was not a good method for analyzing these individual units. So to summarize what this presentation has gone through, this paper has concluded that the adversarial attacks question the robustness of these classification networks, and that these attacks are transferable to different models. And furthermore, they're transferable to different models that haven't been trained on the same data set. And then they give a mathematical basis for these attacks existing, as well as a avenue of research for how to reduce the effect of these attacks. And then the second part concluded that the semantic information is spread among the units as opposed to individual units. And it kind of concludes that analyzing the individual units is more difficult than the prior method would suggest. So strengths for this paper, I thought it had a really good explanations for higher level understanding. Specifically, it related all of its conclusions back to core understandings of deep neural networks, which helps to like more easily apply the knowledge you already have. The experiment design for the second property with units was really simple, and this helps make it a really strong refutation of the method that previous authors had used. And then the results for the attacks were very clear, and they're very strong results, especially for transferability. And then there are widespread implications for these attacks, in particular with transferability. This vulnerability in classification networks wasn't known about. And so for using classification networks for critical systems, it's a very important issue. And then the mathematical analysis that they provided was really useful, especially in creating a further avenue of research for trying to reduce the vulnerability of these classification networks. And now Rahul will talk about the weaknesses.
Okay, and now for some weaknesses. So the two intriguing properties proposed seem to be disjoint to me. They didn't really connect these two properties well. I thought maybe they could have done it in two different papers with better experiments. And then regarding the first intriguing property, the random combination of units, it's not well explained. How is this random combination of units taken? Is it totally random, or is it a Gaussian, or is it uniform distribution? It's not very clear from the paper. And the third one is the weak experiment supporting the first property. This is regarding the semantic information among neurons. They just give one particular figure which shows which supports their claim, but there is really no experiments for that. Adversarial input generation is not detailed. The actual adversarial input generation, the algorithm, it's not discussed in much detail. It's just one section. And then the results from the adversarial training are insignificant. So once they got these adversarial samples, they try to send in this back to the network along with the original clean images to see if it will learn better. But these results seem to be insignificant. It's just an improvement of 0.1% from the paper. And then there's little evidence for extremely low probability of adversarial inputs. So I've taken this line from the discussion section of their paper. They say that these adversarial inputs have this extremely low probability. I don't see any evidence for this low probability of the adversarial inputs. So some thoughts. So they say that the issue of this rugged decision boundary isn't quite addressed. They try to do it by using this adversarial training, but it doesn't seem to be very effective. Can we use the same optimization to retrieve the original label? So right now we have added some perturbation, we have changed the label. Can we again add some more perturbation in some negative way and then try to retrieve the original label back using the same optimization method? Then the other one was, if the number of classes is small, will the problem be less severe? This is also one thought. And then, I feel this paper is really thought-provoking, and then it's a really good paper. And then we're open for questions and discussions.